In this video, I'm going to introduce to you the definition of the natural logarithm in terms of calculus. So given any real number x greater than 0, the natural logarithm of this x is just the value of the definite integral from 1 to x of 1 over t dt. Now I'm using the fundamental theorem of calculus to define the natural log of x as a function of x, because 1 over t is a continuous function over the interval from 0 to infinity, not including 0. So we can define then the natural log of x to be that definite integral. Some consequences then come immediately from the fundamental theorem of calculus. The first one is that since 1 over t is continuous from all numbers bigger than 0, the natural log of x is also then continuous for the same values. Also, it has a derivative over that range of values, and its derivative is just 1 over x. And lastly, the natural log of x, therefore, must be increasing as the derivative is 1 over x, and that derivative is positive if x is positive. So we already know a lot about this natural log just because of the way we defined it. But you might feel better if you learned how to evaluate it. Thing is, though, is that the definition of the natural log is in terms of a definite integral. Our normal way to evaluate definite integrals is to find an antiderivative. But as of yet right now, we don't know the antiderivative of 1 over t, so we can't use that technique. But what we can do is remember that definite integrals really, when they were first introduced, were just limits of Riemann sums. So any Riemann sum will approximate the natural log of 2. So the natural log of 2 then is a definite integral from 1 to 2 of 1 over t dt. In this case, I will use a partition, which in this case is the entire subinterval, and I would choose as my choice point the rightmost x value on the interval from 1 to 2 to get the smallest possible function value, which is 1/2. That means then that the natural log of 2 is essentially more than 1/2 the height of that rectangle times the width of that rectangle, which is 2 minus 1. So the natural log of 2 is more than 1/2. Of course, if you want to, using your calculator, you could just go type in the integration from 1 to 2 of 1 over t dt, and you would then get this particular answer. You'd get this particular answer. But if you want to just type in the natural log of 2, because it's the exact same thing, notice you get the exact same answer. It's neat. So we could then go and look at this in general, evaluate this function, the natural log of x, for various different numbers. I'll use Desmos to show you the result. So here is the function, the natural log of x, and I've also included the graph of 1 over x. As x changes, I sweep out different areas under the graph of 1 over x. I therefore get different values of the natural log of x. So here, if x is 4, the area under the graph of 1 over x and above the interval from 1 to 4, that would then correspond to the natural log of 4, and I plot the point you see in black on the graph of the natural log of x. So as I move x, I wind up tracing out the natural log graph. Neat, right? I'm also going to go over and show you off to the left-hand side, natural log of a and this definite integral from 1 to x of 1 over t dt. See, they're the same value? Because literally the definition of the natural log is a definite integral. Okay, good. So you can see that. The important thing here is that you now at least see why the graph of the natural log of x is the way it is. The domain is still like you learned in pre-calc. It's everything bigger than 0. Its range is also all real numbers. To see that's true, though, I'd have to prove that. I will save that for later on, and instead I'll just put it down in terms of limits. The limit of the natural log of x as x goes to infinity is infinity. So the natural log of x increases without bound. Also, as x approaches 0 from the right, the limit of the natural log of x goes to negative infinity, which means the natural log of x also, if x decreases, the natural log of x also decreases, but without a bound. Since the function is continuous and it goes to infinity on one end and negative infinity on the other, the range has to be everything, all real numbers. Now, it's important to notice that this limit the limit of the natural log of x as x approaches 0 from the right-hand side being equal to negative infinity does not mean the limit as x approaches 0 exists. I'm just describing how it doesn't exist. More importantly, this is the way we said that a function has a vertical asymptote. If, as you take the limit of that function, as x approaches 0 from either left or right, that the function's limit was unbounded. So we now know that if x is more than 0, the natural log of x is continuous. If x is less than 0, the natural log of x is not even defined. And if x is approaching 0, we get a vertical asymptote. So the only possible places for a natural logarithm to have a vertical asymptote is where the argument for the natural log is 0. This allows us to find vertical asymptotes for natural logarithms when we go about their graphs. Also, the other limit says that there actually is not a horizontal asymptote for the natural log of x. This is really important because if you graph the natural log of x, if you look for very large changes of x, like really large x values, it will look like the graph of the natural log doesn't change at all. It will look like it has a horizontal asymptote, but it doesn't. It just takes an incredibly long time to even get to the value of 10 or 20 or 30. Okay, now, combining what we just saw, the definition of the natural log is in terms of a definite integral, but more importantly, we know its range is negative infinity to positive infinity, which means somewhere the natural log of x equals 1. But we also know, since the derivative of the natural log of x is always positive, that the natural log of x is always increasing. So it can only be 1 for only one x value. Because of that, let's define it. We're going to call e the natural number to be the single value in the domain of the natural logarithm so that the natural log of that number is 1. So now you have the real definition of what e is. We'll then come back later on and figure out ways to compute this number e. You know what it is. It's about 2.718 and so on. Okay, so let's go and use what you just learned. Let's look at the function, then f of x equals 1 plus 3 times the natural log of x minus 4. Let's find its domain, let's find out where it's continuous, and let's find the vertical asymptotes of its graph. All this is very easy. It's exactly what you learned before. The only difference is now is that you now have reasons for why you should do what you do. So the domain of the natural log is only positive numbers. So you can only let the input for a natural logarithm to be positive. Now, to define the domain of a function, you're looking for normally where do you have a potential division by 0, where do you potentially have a even root of a negative number. Here, though, none of those exist. The only one that exists, though, the only limitation on the domain comes about because of the natural logarithm. So, in this case, to find the domain, I'm going to solve that x minus 4 is more than 0. That way the natural log is defined. So that's clearly x is more than 4. So the domain is then the set of all numbers bigger than 4. Easy. Now you might want to know where is it continuous. Well, see, the natural log is continuous on its domain, and x minus 4 is continuous everywhere. So the natural log of x minus 4 is continuous wherever it's defined. And then 3 times that is also continuous, because you can always take a multiple of a continuous function and the result is continuous. And when you add 1 to it, it's still continuous. So then the only place that you could really not have continuity is where that function is just not defined. So where this function is defined is where it's continuous. So this function, f of x, is continuous from 4 to infinity. That means then if you wanted to graph this function like you did in pre-calc, you would plot a bunch of points, and then you would just go connect the points. Now, you might wonder then where the vertical asymptotes. Well, that's where we need to know this guy. So we know from this statement then the only possible place where we can get a vertical asymptote is where the input is near 0. So to find my vertical asymptotes, I'm going to to find the vertical asymptotes, I'm going to solve that x minus 4, the input for the natural log is 0, which means x equals 4. And that's it. That line is the only place where we can get a vertical asymptote. And we do. If x is near 4, you'd have the natural log go something near 0, and that will go negative infinity. All right, great. Now, let's go and do some more calculus then stuff. I'd like to know then, what are these limits? Just don't forget how to do these particular limits. This limit here and this limit here. We'll need both of them in order to do the limits I'm giving you. So to find the limit of 3 minus the natural log of 4 minus x squared, well, if x is approaching 2, then this is approaching 4. This then is approaching 0. We have to be careful, though, and to figure out how does it approach 0. So if x approaches 2, but it's less than 2, this is less than 4. This difference then is more than 0. So then this is approaching 0 from the right. That means that this then, based upon our fact right here, that means that this approaches negative infinity. So I have 3 minus something approaching negative infinity. That would then approach positive infinity. 3 plus positive infinity. That would then be, of course, infinity. This is asymptotic analysis. There really is no work. Okay, the next one. Now, once again, I'm going to need these facts in order to get the answer. So I want to know what's the limit as x approaches 3 from the right. Well, if x approaches 3 from the right, then this here approaches 0 from the right, because it's always more than 0. So then this approaches negative infinity. So the denominator is 2 minus infinity. That approaches negative infinity. You then 5, a constant, over infinity. Based upon work that we've done before in Calc 1, we could then say that limit actually approaches 0. A constant over infinite by using asymptotic analysis, that is 0. Cool. Last one. All right, so then I need to know what's the limit of this particular function here. Well, if x approaches infinity, this approaches infinity, that approaches infinity. So then the limit is infinite over infinite. I can't write that down. That's another one of those indeterminate forms. So I need to use those little tricks you learned from Calc 1 earlier on in the course. The trick here is to rewrite this once as the limit as x approaches infinity, and to divide everything by the term that grows fastest in the denominator. In this case, the only term that changes in the denominator is the natural log of x. Just divide everything by that. So natural log of x divided by natural log of x, 1, plus 5 divided by natural log of x. That's all over. Natural log of x divided by natural log of x, that's 1, plus 2 over natural log of x. And then this is by asymptotic analysis. This is going to 5 over infinity, that's 0. This approaches 2 over infinity, that's 0. You have 1 plus 0 over 1 plus 0. That limit then in the end is going to be 1. And that's the answer. Pretty simple, right? Now that we have the derivative of the natural log, we can then use it in a composition with another differentiable function, u, to find the derivative of the natural log of u. By the chain rule, that's just 1 over u times the derivative of u in terms of x. Put shortly, it means to take the derivative of the natural log of u, put the u in the denominator, take its derivative, put it in the numerator. It's a great rule. So as an example, if I want to know what's the derivative of the natural log of 5x, I would have 1 over the argument for the logarithm, that's 1 over 5x, times the derivative of 5x, which is just 5. So that would then be 5 over 5x. That's 1x. That's 1 over x. So what if I wanted to know what's the derivative of the natural log of x squared plus x? So by the rule, I would put the x squared plus x in the denominator. I would multiply it by that derivative and put that in the numerator. So the derivative of x squared plus x is 2x plus 1. So the derivative of the natural log of x squared plus x is 2x plus 1 over x squared plus x. It's, again, a great rule. But there's something more we need, and we can get almost for free. So I want to know then, what's the derivative of the natural log of the absolute value of x? Now, lots of students will then say, but Professor Dugan, the absolute value of x, we know, does not have a derivative at 0. True, but we're never using x as 0 because we're taking the natural log of it. So that never occurs. You don't have to worry about that at all. Let's just find this derivative. Now, to do so, a very common method to find anything that's complicated in calculus is to rewrite it in such a way that it falls back upon earlier rules. So we know how to write the absolute value of x various ways. We can replace the absolute value of x when x is positive with just x. And if x is negative, we can replace the absolute value of x with negative x. So I'll just do these two separate derivatives in the two separate cases. Well, but the derivative of the natural log of x, you would put the x in the denominator and take its derivative, 1, and put it in the numerator. But the derivative of the natural log of negative x, you would put negative x in the denominator and take its derivative, negative 1, and put it in the numerator. But notice that it doesn't matter. It doesn't matter if x is positive or negative. Either way, these two derivatives in the end simplify to the same thing. It's 1 over x. So that means then that the derivative of the natural log of the absolute value of x is 1 over x. Most students then say, wait a minute, but how can they have the same derivative? Yeah, it's possible. Happens, sure. Functions can have the same derivative. Sure, it's fine. Now, but why do we do it then? The reason is that the function 1 over x, its domain is everything but 0. But the domain of the natural log of x is only bigger than 0. Those two things don't have the same domain. But here, this domain of this function and the domain of this function, they are indeed the same thing. So, because of that, we're going to be using this a lot more. You're going to see this quite a bit more. Now, we could then extend this out a little bit, because if u is a differentiable function, then by the chain rule, the derivative of the natural log of the absolute value of u is 1 over u times the derivative of u in terms of x. In other words, when you take the derivative of the natural log of the absolute value of u, drop the natural log, drop the absolute value, just put u in the denominator, and take its derivative, put it in the numerator. This is usually something that upsets people, because they wonder, where did the absolute value go? To those students, I say, yeah, but where did the natural log go? It goes too, right? It vanishes. So it's okay to lose functions when you take derivatives. Let's just practice it to make sure you understand what I'm doing. So the derivative of the natural log of the absolute value of 5x, forget the natural log, forget the absolute value, just drop them. Take the 5x, put it in the denominator, take its derivative, put it in the numerator. You would then have 5 over 5x, and that's 1 over x. What about the derivative of the natural log of the absolute value of the secant? So just drop the natural log, drop the absolute value, put the secant in the denominator, take its derivative, secant times tangent, and put it in the numerator. But then you would have secant of x times tangent of x divided by secant of x, and that's tangent. A little bit more complicated one. I'd like to know what's the derivative of the natural log of the absolute value of the secant of x plus tangent of x. So by the rule, don't you just ignore the natural log, just ignore the absolute value, put the secant of x plus the tangent of x in the denominator, and put its derivative, secant of x times tangent of x, plus secant of x squared, in the numerator. And then notice in the numerator, see there's a common factor of secant? Once you take that out, there's now a common factor in numerator and denominator of secant of x plus tangent of x. They cancel, giving you secant of x. So after all this, the derivative of the natural log of the absolute value of the secant of x plus the tangent of x is actually just the secant of x. This has a really neat consequence, and if you want, we can keep doing the others, but it winds up being that here are the weird functions whose derivatives are the other trig functions. We know the function whose derivative is cosine, it's just sine. We know the function whose derivative is sine, it's negative cosine. But unfortunately, the other functions whose derivatives are either tangent, cotangent, secant, or cosecant of x are not nice. They all have natural logs in them. Now, we don't really need to memorize these rules because we know the derivative of the natural log, but these are very nice for later on when we do integration. So now, speaking about integration, so the derivative of the natural log of the absolute value of u is 1 over u times the derivative of u over in terms of x. But that implies then, by undoing that derivative, that the antiderivative of 1 over u du, that form is the natural log of the absolute value of u plus the constant of integration, assuming u is a differentiable function of x, of course, or else you can't do any of this. Now, in particular, if you think of it in terms of substitution, if u actually was f of x, this means that if you ever see an integral that has a fraction form to it, that's this guy right here, fraction form, where the derivative of the denominator is the numerator, this says then you should use this substitution, and the result will then be this answer. It's always going to be the natural log absolute value, don't forget that part, of what was in the denominator. I think we should probably practice this a few times. So let's just try it. I want to integrate this by using u substitution. So to do so, I would let u equal to 2 times the sine of x plus 1. Then du is then take the derivative of u in terms of x, which is here 2 cosine of x, and multiply by dx. I'll now rewrite this once as the cosine of x dx, and I'll multiply this by a half on both sides. That then allows me to say, after these substitutions, that integral becomes the integral of a 4. The cosine of x dx becomes 1/2 a du, and the 2 sine of x plus 1 is a u. Simplifying that becomes the integration of 2 over u du. You can think of it like the 2 comes out first. You then are integrating just 1 over u in terms of u, and that is the natural log of the absolute value of u plus c. Well, we know what u is, so that's 2 times the natural log absolute value of 2 times the sine of x plus 1 plus c. And that's the answer. Really easy, right? Very similar to what you've already done. Let's try it again. This time we'll have bounds. So I want to know what's the definite integral from 2 to 4 of y squared minus 3 divided into 6y. The very first thing I would do is just convince myself that even exists. So notice that y squared minus 3 on the interval from 2 to 4 is never 0. So the integrand is never 0. The integrand, always exists. And in fact, it's a division of two continuous functions. So that does indeed have a value. If I was integrating from, say, 1 to 2, I couldn't say what this is. It wouldn't exist, probably. We'd have to do something else to figure out the answer, if it exists at all. But over this interval, we're fine. So I'll go and use u is going to equal to y squared minus 3. Then du will be 2 times y dy, which means that y dy will then be 1/2 a du. Also, at the same time, I'll have u values and I'll have y values. Y values are 2 and 4. And I can find the corresponding u values by just evaluating u in terms of those y's. So when y is 2, u is 2 squared minus 3, that's 1. And if y is 4, u is 4 squared minus 3, that's 13. So based upon these substitutions, this then becomes the definite integral from 1 to 13 of 6, and the y dy becomes 1/2 du, and the y squared minus 3 becomes u. I'll just clean that up. That's the same as writing a 3 over u du from 1 to 13. That then is, the constant 3 just comes out. You then integrate 1 over u in terms of u, which is the natural log absolute value of u. Here, though, we don't put plus c because we have bounds, so I'll evaluate it from 1 to 13. So we plug in 13, we plug in 1. You get 3 times the natural log of the absolute value of 13, which is just 13, minus 3 times the natural log of the absolute value of 1, which is 1. But that is just this, 3 times the natural log of 13, because the natural log of 1 is just 0 anyway, so just ignore it. And that's that integral. Now, based upon the derivatives you've seen, you saw the derivative of the natural log of the absolute value secant was just tangent. That then implies that because of this fact, that the integration of the tangent is unfortunately something that has a logarithm in it. So what I've done for you is I've written down all the positive versions of these integrals. These are all antiderivative rules that you need to memorize. It winds up being, though, that there's so many funky, weird things you can do. You can rewrite trig functions so many ways. There's also properties of logarithms that allow them to be rewritten lots of ways. That there's alternate forms of all of these. So the natural log of the natural log of the absolute value of the secant of x plus tangent of x is actually the same as the opposite of the natural log of the absolute value of the secant of x minus the tangent of x. The natural log of the absolute value of the secant is actually the same as the opposite of the natural log of the absolute value of the cosine, and so on. So these are the positive versions of the integrations. These are the negative versions. I suggest you memorize 1 pair for each. Don't memorize multiple pairs. It's just confusing. Myself, I memorized these because these wind up being easier for applications. Your book suggests you use this one for the integration of tangent. For the integration of the cosecant, I actually use that one. And for the integration of cotangent, I actually use that one because that's just how I was taught way back when. But if you want to use these forms instead, you go right ahead. It really is up to you. If you just want to make sure that there's never a negative in it, they just use everything to this side of the line. All these, just use these guys instead. Okay. Let's just try it. So I want to know what's the antiderivative of x squared times the secant of 3x squared, of 3x cubed. Not difficult to do. I'd let u equal to 3x cubed. Then du would then be 9x squared dx. That means that x squared dx is really 1/9 of du. That then equals, by using these substitutions, to be the integration. I have a secant of u, and the x squared dx, that's the 1/9 du. I'll put the 1/9 in front and the du in back. So that equals then 1/9 the antiderivative of the secant of u, which we know is the natural log absolute value of the secant of u plus the tangent of u plus c. So the final answer then is 1/9 natural log absolute value of the secant of u, which is 3x squared, plus the tangent of u, which is 3x squared. All in absolute value plus c. That's the answer. Not difficult, right? Again, it's very similar to what you've already seen. You just have some new antiderivative rules to memorize. Okay, let's try this one. I want to know what's this antiderivative. This one's a little sneakier. Not much, but a little bit. Here, I'd let u equal to x squared minus 2x. Then du would be 2x minus 2 times dx. Notice I can divide both sides by half to get 1/2 du equals x minus 1 dx. So based upon these substitutions, the integration then becomes, that's the integral of, in the numerator, that's x minus 1 times dx. That's the 1/2 du. And the denominator then is the sine of u. I'm just going to clean that up a little bit. You can write this as the integration of 1 over 2 the sine of u du. Now, unfortunately, though, I still have a division. I have a division of sine of u, and we don't have an integration rule for that, not division. So we're going to rewrite that once as the integration of 1/2 and use the reciprocal of sine being the cosecant of u du. That we have an answer for. So this then equals 1/2 natural log absolute value of cosecant of u minus cotangent of u plus c. That's one of the two forms of that particular antiderivative. We can then replace what u is equal to. So the final answer then is, unfortunately, I have to bring it way over here to get room on the page. The 1/2 the natural log absolute value of the cosecant of u, which is x squared minus 2x, minus the cotangent of u, which is x squared minus 2x, plus c. And that's the answer. All right, one last one. This time we're going to have bounds. I want to know then what's this particular definite integral. Once again, we'll just use definite substitution. So let u equal to 2x. Then du is going to equal to 2 dx. So our dx is really 1/2 of du. Also, I have bounds, so x and u. X could be 0 or pi over 6. So I can find the corresponding u values by just plugging in 0, plugging in pi over 6. If I plug in 0, I get u is 2 times 0, which is 0. And if x is pi over 6, I get u is twice that, which is pi over 3. So then based upon these substitutions, this then becomes the definite integral from 0 to pi over 3 of the tangent of u du. And we know the antiderivative of the tangent of u. That is then equal to natural log absolute value of the secant of u, and we evaluate this from 0 to pi over 3. So that is the natural log absolute value of the secant of pi over 3 minus the natural log of the secant of 0. Okay, so that's then the natural log absolute value of, I need to know the secant of pi over 3. So I need to know the cosine of pi over 3. The cosine of pi over 3 is just 1/2. So then the secant's reciprocal, that's 2. Minus natural log absolute value. I need to know the secant of 0. So I need to know the cosine of 0, which is 1. The reciprocal of that then is the secant of 0, which is also 1. So the answer then is the natural log of just 2. Because the natural log of 1 is just 0. And the absolute value of 2 is just 2. So you get the natural log of 2. And that is it. Now that you have the definition of the natural log of x, and you have its derivative, you're going to start finding it in integrals also. As a rule of thumb, if you ever see a natural log of x, or really any logarithm in an integral, pretty much instantly try that first. Make u be the natural log of x and just see where it goes. So here, for example, if I wanted to take the antiderivative of 5 over x times the natural log of x, if I let u equal to the natural log of x, then du would equal 1 over x dx. And you can see if you rewrite this just a little bit, this is really a 5 over a natural log of x times a 1 over x dx. So the substitutions then are obvious. This then becomes the integration of 5 over u, and 1 over x dx, that's just du. Now the answer hopefully is easy. That would then be 5 times the natural log of the absolute value of u plus c. But we know what u is. It's the natural log of x. So that's 5 times the natural log of the absolute value of the natural log of x plus c. And that's the answer. Let's just do it again. So in this second problem, I want to know what's the integration of the natural log cubed of x divided by 4x. The minute I see a logarithm, I'm going to try u equals the natural log of x and just see where it goes. So I'll make u equal to the natural log of x. Notice, though, that the work here is the same as above. So instead, I will just rewrite this a little bit to make it obvious for you. This is really the integration of 1/4 times the natural log of x. This is actually cubed. Times of 1 over x dx. Being able to mentally rewrite things this way makes it a lot easier to understand. This then becomes the integration of the constant. The natural log of x is just u. It's being cubed. And the 1 over x dx, that's just du. So that would then be, you'd get 1/4, take the u, increase the power, multiply by the reciprocal of the power, and add c. So the answer then is 1/16 u to the 4th plus c. But we can replace what u is, so that this then equals 1/16. It's the natural log of x to the 4th power. You put the 4 there. And then plus c. That's the answer. That's the antiderivative. So now you see, if you ever see a logarithm, natural logarithm, other logarithms in an integration, one of the first things you almost always try is just make u be that and see what happens. Okay, now just going over some pre-calc again. There are some properties of logarithms that we can prove based upon the definition I've given you from calculus. I'm more interested right now in just teaching you how to use them again to remember. I will have a separate video on the proofs of various facts, so you see why these things are true based upon only the definition. But we need them for calculus reasons. A very common thing in calculus is to rewrite things before you do an operation. Well, it happens to be that the logarithm has all kinds of really nice properties that allows you to rewrite products and quotients and powers. So, for example, if I wanted to know a way to rewrite the natural log of x squared sine of x by one of the rules, this then becomes the natural log of x squared plus the natural log of the sine of x. And then by, again, one of those rules, you can take the power out here, get the natural log of just x plus the natural log of the sine of x. Now, you don't really need parentheses here. It's understood that if there isn't product or quotients or if it's just one expression, it's understood to be the natural logs applied to the sine of x. You don't need the parentheses. But if you want to include them, you can. Do it again here. The natural log of 2x plus 3 divided by x minus 4. That would then be the natural log of 2x plus 3 minus the natural log of x minus 4. Here, the parentheses are necessary because without them, it's not clear what the natural log applies to. So with the parentheses, it's now clear the natural log is applied after you take 2x plus 3. Good. So that's rewriting logarithms. We're going to need that skill to make differentiation a little easier for us. Because if you ever have to take a derivative of a natural logarithm where the logarithm is applied to a product, quotient, or power, you always rewrite first. If you don't, it's truly awful. So again, you always rewrite before you take a derivative of a logarithm that's applied to a product, quotient, or power. So for example, here, I could write this as, instead, the natural log of x plus 1 cubed times x minus 2, where this entire thing is to the 1/2 power. So I can take the half power out, get the natural log of the x plus 1 cubed times x minus 2. And again, it may not be clear what the logarithm is applied to, so I'll put that in parentheses also. But then that is 1/2. The natural logarithm is now applied to a product. So that becomes a sum, a natural log of x plus 1 cubed plus the natural log of x minus 2. But then that, when you take the natural log of x plus 1 cubed, you can bring the power out and get just x plus 1 times a natural log of x plus 1 times 3, plus then you still have the natural log of x minus 2. this will be a lot easier to take the derivative. So the derivative of f in terms of x would then be, I have the derivative of a constant times a function. So the constant comes down first. I then multiply by the derivative to the sum. The derivative of a sum is the sum of derivatives. So I take the derivative then of the first part of that sum, 3 times the natural log of x plus 1. I put the constant multiplication down first. And then I take the derivative of the natural log of x plus 1, which is the x plus 1 goes in the denominator. Its derivative goes in the numerator, plus. Now I need the derivative of x minus 2, the natural log of x minus 2. The x minus 2 goes in the denominator. Its derivative, 1, goes in the numerator. And that's the answer. You can clean it up. You could write it as 1/2 times 3 over x plus 1 plus 1 over x minus 2. But I would leave it that way. I would leave it that way. If you want to add the fractions to get a common denominator, okay. I wouldn't. It's probably easier to deal with it the way it is. But if you really want to, you could. Okay, good. So that's the derivative. Don't forget this. If you ever have to take the derivative of a logarithm that's applied to a product, quotient, or power, always rewrite it. Always rewrite the logarithm applied to the product, quotient, and power using logarithm rules first, and then take the derivative afterwards. If you try it the other way, you'll see why. Okay. Now, how can we use this nice little fact? This means then that if you really, really, really want to, you never again have to use a product rule ever again. You never actually ever again have to use quotient rules. You can use a process called logarithmic differentiation. It is one of those, it's a technique that people know about that they almost always forget because you just don't use it that often. Because in homework on tests, we can't give you truly awful derivatives. I'd love to, but we just can't because it would take too long for the bulk of students. We want to make sure we know the basics on a lot of these tests questions. So here, though, I can use logarithms to rewrite the equation first in an implicit form and then differentiate that instead. So, for example, the first step here to find this derivative using the process of logarithmic differentiation is to take the left and the right hand side and just take the natural log of it right away. Natural log of the left hand side equals natural log of the right hand side. Okay, now y. I'm going to take this up here for a minute. That would then be the natural log of y equals, well, the natural log to a quotient is found by taking the natural log of a difference of the natural log of the numerator and the denominator. So I take the natural log of x plus 2 squared minus the natural log of the product x times 3x minus 1. But that means then you get the natural log of y equals, this is 2 times the natural log of x plus 2. Then you have minus, the natural log of a product is a sum of logarithms, but the negative distributes through that sum, so they become subtractions. Get the natural log of x minus the natural log of 3 minus x minus 1. There you go. Now I know you look at it and go, wow, that's really intense. That's really awful. There's so many logarithms. That's okay. This is the whole point of this, is to give you an option to take this path. So you need to know how to do it. But it's, again, one of those skills a lot of students forget because they choose not to do the technique. All right, so then to find the derivative from here, y was a differentiable function of x. Remember, it was back here in the beginning. It was back here in the beginning. So we know this thing has a derivative in terms of x. I just got to find it. So this entire expression, I can take its derivative all the way through implicitly in terms of x. So let's just do that. I then take the derivative of the left-hand side of that equation in terms of x. The derivative of the natural log of y in terms of x is, by the chain rule, 1 over y. You put the y in the denominator. You take its derivative in terms of x and put it in the numerator. So that will then be dy dx. Or if you want, you could write y prime. That's fine too. That then equals, now I take the derivative of the right-hand side. That'd be 2 times the derivative of the natural log of x plus 2 would then be x plus 2. And then put that derivative in the numerator. Then you have minus. The derivative of the natural log of x is put the x in the denominator. Take its derivative, put in the numerator. Then you have minus. The derivative of the natural log of 3x minus 1 of the natural log, the absolute value of the natural log of 3x minus 1 is put the 3x minus 1 in the denominator. Take its derivative, 3, put it in the numerator. And that is me differentiating in terms of x. I can then solve, if you remember doing implicit differentiation, we then solve for the derivative to get dy dx, the thing we were trying to find, is equal to, well, that's a 2 over x plus 2 minus 1 over x minus 3 over 3x minus 1, and that's times y. And that's the answer. That's what the derivative is. It's just in terms of x and y. Now you may feel unsatisfied because after all, y is in terms of x here only, so the derivative should be in terms of x only. It is actually, because the y here is a function of x, and we actually know what it is. So I can do one more step and replace the y. That then gives me 2 over x plus 2 minus 1 over x minus 3 over 3x minus 1 times y, which is x plus 2 squared, all over x times 3x minus 1. And that's the answer. That's what the derivative is of y in terms of x. Now, you might look at it and go, but yeah, but now look at all this. I have to simplify all this. Yeah, that's why we don't use this very often. We don't use logarithmic differentiation very often because it does make the derivative a lot easier. You don't have a quotient rule anymore, right? There's no more product rule. There's barely use of a chain rule. The actual act of the derivative was really easy. But then the algebra is really bad. So if you want to use this for anything other than just to evaluate the derivative, I would not use this technique. So it's nice to know. You should know about it. It does make certain problems later on a lot easier, but very, very seldomly do we actually use this technique. And that's the end of the presentation. After this, in a classroom atmosphere, I would normally go over some proofs to show you the main reasons behind the properties of the logarithm, why the range is the way it is, and so on. But I'm going to put them in a separate video at some point. This then presentation goes over the basic definition of the natural logarithm in terms of integration. It gives you the definition of what the natural number e actually means. It also goes and reviews a lot of pre-calc, so you know how to evaluate, how you know the graphs of the logarithm, you know how to find the vertical asymptote, you know how to find its domain, you know how to find out where the function is continuous and not. You know how to integrate functions 1 over x or many other fractional forms. You know the antiderivative of sine, cosine, and also now secant of x, tangent of x, cotangent of x, and cosecant of x. Next video, we then extend this and talk about the inverse function, the natural exponential function.